Okay, excellent. Good. Okay, so let's start. You can hear me there at the back? Can you hear me? Oh. Can you hear me at the back? Some of you are too busy, so you can't even hear that I'm asking if you hear me. Okay, so I want to talk a little bit about the problem sets, and what I've seen consistently is that things that I do mention in class, and some of you ask questions about in class, are being asked again in Piazza. So either you don't listen. I'm talking to the two people at the back that are very busy with the laptop. Yeah, you're one of them. If you listen now, I think it reduces the chances that you will ask the same question again, and in general reduce the chance for confusion. So I want to address issues in previous problem sets and mostly in future problem sets. So please stay with me. So first of all, homework 1, this is what you had, which I think is pretty nice. I know that you worked hard on it, but overall, the average is close to 90. Quite a few of you did not submit homework 1. I don't know why. At least I'm looking at the gap between the people that are registered and the number of submissions. So if you chose not to do it, it's okay. But I think you should work on it. I think you'll typically learn a lot from the problem sets. What you will find on the website next to homework 1 is the rubric that the TAs used for grading, and also some comments, general comments about the problem set. I think they did an excellent job, and also did it very quickly. So please look at it, ask questions if you have any. 2. Unfortunately, we had some issues with homework 2 that we could have defined better. But in terms of grading, don't worry. I mean, you'll always get the benefits of the doubt. If there was something that wasn't completely clear, either way you chose to do it will be acceptable. The thing that I regret most about homework 2 was that the data was a little bit too easy, and therefore some of the things that I wanted you to observe, you couldn't observe so well. So we worked very hard on homework 3 to make sure that this is not going to happen. This is why it was a little bit delayed, but I think it's perfect. We'll see in a few days if you think so too. But the issue is that we also notice that we also extended the due date. So you haven't lost anything. Question? This is something I addressed several times in the first few lectures. It's typically A. Most of you, if you work very hard, you should get A, right? If you don't work hard, you will get less than an A. But that's, is that satisfactory, or you want more details? No, but seriously, I mean, I think a large percentage of the people that continue with the class and do a good job is going to get an A, some kind of an A. I'm not saying that all of you will get an A, right? But I'm saying that all the people that keep up with the class and do a good, pretty good job will do. So, okay, so again, the numerical scores don't necessarily tell the truth. But I think that overall, I'm pretty happy with what happened. Okay, I want to talk about homework 3. Homework 3 is really very, very simple conceptually. It's going to take you a little bit of time for two reasons. First, because it takes time to realize that it's actually conceptually simple. And also, you will have to run stuff. It's not your time, it's typically CPU time, especially if you do it, if you think a little bit before you start doing it. So here is what you have to do. Or these are the lessons first. I want you to understand online algorithms. So there are 3 algorithms, perceptron, Winnow, and AdaGrad. In fact, 2 versions of perceptron, 2 versions of Winnow, and only 1 version of AdaGrad. Even understanding this, you've already learned something, because we explain in the problem set why, for example, there is only 1 version of AdaGrad. Now, as you will notice, the first thing you have to do is implement these algorithms. It's very easy to implement this algorithm. It's really the same algorithm with, depending on how you implement it, between 1 and 5 lines of codes that are different. So once you think about it, you see that the implementation is really easy. It doesn't matter how you implement it. And the second lesson is understanding how to run experiments in machine learning and learning from the experiments, because you will learn a lot about these algorithms and in general about learning experimental work in machine learning from doing it. So in particular, you'll have to tune parameters, because algorithms have parameters that have to be tuned. And you'll have to do comparisons and draw some conclusions from this. So this is, so here, there are conceptually 2 extreme ways of doing it. You're going to run a lot of experiments. You can sit in front of the terminals and run experiments, or much, much better, as you understand what you're about to do, write a script. You can do it 17 different ways, but you have to be organized and write a script that runs your experiments. And then you can go to sleep, and in the morning, you can draw conclusions. So really, I really think that if you are organized, the time that you have to spend programming here is a couple of hours. You'll probably spend a little bit more, because it will take you time to figure out how to be organized, unless you have experience with this, but not a lot more. And it will take time to run some of the experiments, again, depending on how many times you want to do it and what machines you're using. Yeah?
There are some tools from MIT that make it very...
I wouldn't run it on your laptop, sorry. It's much easier, unless you're an expert in some other external tools, run it on your laptop, because I don't want you to spend 10 hours learning additional tools. Now, if you are an expert in some other things, do whatever you want. But from the perspective of the problem sets, it's easy enough. And it will just take twice more. It's not, nothing is going to be expensive. Okay, so what's the assignment? The assignment is to learn. Who has already looked at the assignment on the web? Okay, excellent. So most of you know something. The assignment is to learn linear functions that we call LMN functions. Deliberately, I colored the N by red, and I left the other. So what's the difference here between LM and N from your perspective? almost. The answer is, the suggestion is n is the same for everybody. Yeah? We know n. That's it. So n is just the dimensionality of the problem. This is the data. It could be 100, 500, 1,000, whatever we ask. We know n. Everyone knows n. The learning algorithm knows n. M and L are not known. Now, it's not the same for everyone because we're going to ask you to generate different data sets with different n's. But once you fixed n, then everyone knows it. L and M are not known. Well, they are known to the program that generated the data, but they are not known to the learner. And this is the challenge here. You will have to learn something. In fact, as you will notice, you will actually not learn directly, at least, L and M. You will learn a linear threshold function that is going to perform well, but will not output in any way explicitly M or L. But this is the key thing. So you know M. What you have to do is this. You have to implement the algorithms. You have to generate the data. We gave you a MATLAB program that generates data. You'll have to do it multiple times. But I think it's completely clear what to generate. You have to think because you have to devise a plan for what you're doing. And it's, in general, a good advice to kind of think as you're working on these things. And then you're going to run 3 experiments. In each experiment, you will start by generating data. The first 2 experiments, if you noticed, are online learning algorithms. So you generate data once, and you use it. In the third experiment, it's a batch scenario. So you actually generate 2 data sets, one for training and one for test. Okay? So again, in the first 2 experiments, you generate once per setting, right? So there are multiple settings that we give you. But per setting, you generate the data once. And only in the third experiment, you have to generate twice. And then we also added the notion of a noise. So only in the third experiment, when you generate the training data, you add this flag there that says generate noisy data, and then separately you generate the test data. Now, you need to tune parameters. Algorithms behave very differently depending on the parameters. You will notice some interesting things that we point out in the body of the problem set. One of the first interesting things is that for perceptron, the way we set it up, you don't need to tune parameters. But for all the other 4 algorithms, you will have to tune parameters. And we actually tell you what are the parameters you tune. And we also give you which values to try. So in real life, you will not know this. You may guess some range of parameters, and you may guess a step size that could be linear, could be exponential, could be. We already did that for you, and we suggested different values. Notice that in almost all cases, it's an exponential step size. So, for example, you will try alpha, which is 1, 1.1, 1.01, 1.001, and a couple others. So now you tune parameters for every training data set. So of course, if we give you n, you have to tune parameters for this dimensionality. Moreover, if you generate 2 training sets, which you'll do in experiment 1 and experiment 2, each training set deserves a different tuning because, it could be completely different data. It will be completely different data. How do you tune? You generate the data, let's say 50,000 examples. The procedure for tuning that we suggest is as follows. Again, it's a very simple procedure. You code it once, you run it many times. You can, if you do it right, your tuning parameter should take the name of the algorithm as a parameter, and then you just run it 5 times for the 5 algorithms. But again, we decided not to give you code because we felt that it's more confusing than not. So you'll just do it the way you feel comfortable. But basically what you will do is for each training data set that we give you and for each algorithm, you run the procedure. The procedure is as follows. Sample 10% of the data. I don't care how you sample. Call this D1. Sample another 10% of the data. Call it D2. The second sample has to be distinct from the first. That's the only requirement. How you do it, I don't care. And then you run each algorithm with each parameter set on D1. And we suggest to cycle through this D1 20 times because it's a relatively small data set. Just run through it 20 times. You learn the model. Take this model that you learned, evaluate it on D2, record the accuracy. Do this for the second set of parameters and so on. And choose the set of parameters that gives you the best performance on D2. You're done with tuning. Now you have an algorithm. Yeah. In principle, it could happen. I don't think it will happen. So we gave you parameters that we think are reasonable. So you should get we chose parameters that are in the right range. So you should get reasonable performance. Yeah.
What if there are multiple parameters?
Again, it will not happen. You know, you run it on, 10,000 examples 20 times. I doubt this, and with very different parameters, you will not get identical results. If you do, choose randomly. So once you've tuned the parameters, you actually have an algorithm, right? Before, you just didn't have an algorithm. You had something that was parameterized by gamma or by eta or by both of them. Now you have an algorithm. Now you can run the experiment. So the experiment is relatively simple. You basically run it, whatever we ask you to do. So as I said, in 1 and 2, you basically run online algorithms, get a number, and you plot these numbers. And we specifically ask what to do. I think 2 plots in experiment 1 and 1 plot per data set in 2. In 3, you have a batch setting. In principle, as we said there, you should have tuned another parameter, which is a stopping criteria, right? So you train your algorithm. Eventually, you're going to test it in a different setting on the test data set. So you should have decided how many times should I run it. We spare this level of tuning from you, and we just told you run it 20 times. I think it should be enough. If it's not enough, you can also try other numbers. The only thing is that if you do something different, just record what you're doing and put it in your report. Okay, so then you will see results, and I think the results will be interesting in the sense that you will see differences. And you'll have to think a little bit about it and see and to understand what you see. Questions? Okay, so as I said, I think that if you plan your way, it's really not a lot of coding, and everything has to be automated. You know, this is one of the lessons that I want you to learn here. You can't just sit in front of the terminal all the time. I mean, you can sit at the beginning to see that things are doing what you want them to do, but at the end, you know, if you want to run a lot of experiments, you have to be organized, know what you run, and let it go. So there was already a question in Piazza about cross-validation. We didn't mention any cross-validation. It's really simple, and I'm hoping that everything is clearly specified there. We might have missed something, but so please ask. But I think that it's pretty clear. Okay, so I think it's due on Friday next week. So okay. Final comment before we start learning new things. Projects, I just wanted to remind you that I think Thursday, the 9th, is the due date for project proposals. You've already seen this slide, nothing new here. Here are some new ideas or additional ideas. The top one is a new idea. You can do anything you want. Here are a few others. So this is actually something that I've seen earlier. So about footstep recognition, you can do a project on footstep recognition if you want. Here are a few other ideas. You know, identify multi-word expressions. You can build a program or some functionalities for a conference program chair. For example, identify whether the paper is anonymous or not. Not so simple if you think about it. Because if the author is George Bush, it's anonymous. Right? So you can identify authors, assign editors to a paper. You know, there's a lot of subtasks that you can think about. You can think about Twitter. People like Twitter. There's a lot of interesting machine learning problems in Twitter. These are simple and straightforward, at least in terms of definition. I'm not saying that they're easy. This is a little bit hard or harder because you have to parse it, and maybe you can draw some conclusion about who's sending this tweet as a function of this parse. So, okay, so a lot of options for projects. Yes? My preference is that it will be 2, up to 2. If you have very good reasons to do 2.5 or something, then let me know and we can talk about it. Okay. Questions? Yeah.
Do we have some sample proposals?
No. Write a page and a half, explain what you want to do, give at least 2 references of papers that are related to what you want to do, that you've looked at, that either you want to improve on or you want to learn from or something. That's it.
So I have an idea that some kind of the data, but I don't know.
That's fine. That's fine. So you don't need to know everything, and you don't need to solve the problem, but you need to know what you're planning to do, define it properly, so we can make sure that it's doable. And as I said, read some of the literature at least, or sample the literature so that you'll know what's been done on this problem before, who's done it, how did they do it. You don't have to necessarily make all the final decisions. It's just a proposal now. But I wanted to do the proposal relatively early, so now you have 2 months to work on it.
So, like, because using already had my hands out and with the
You don't necessarily have to have done some work, but if you have the data, or you know which data you're going to use, and you know that there's some more work in acquiring the data or annotating the data or doing something, this should be part of the project description. So, just apply your common sense. Assume that you're reading this proposal, and you didn't know 5 minutes ago anything about the project, and try to figure out whether what you've written is a good enough description of what you will do. Right? So, if you cannot test your own 1.5 page, ask your friend to read your 1.5 page and make sure that it's a reasonable explanation of what you want to do. It's really common sense. Okay. Oh. And I will not have office hours today. I'll move it to Thursday instead. Sorry about it. Okay. So where are we? So I actually changed a little bit the order of things. And the reason I'm not continuing directly with what I started last time is that I want to make sure that long enough before the midterm exam, which is in about 3 weeks, we finish something that I want to finish. So I permuted the order a little bit. So we're going to start talking today about computational learning theory. So where are we? We talked about algorithms. We talked about models. But we don't know a thing about generalization so far. So we don't know how will the algorithm that we've learned do on the next example. Right? So what we know is we know something about mistake bounds or things that are related to mistake bounds. It turns out that we will go back to the same algorithms or some versions of the same algorithms, but we will be able to develop on the way some theory that will give us some idea on how to develop guarantees and what kind of guarantees one can develop. Okay, so that's where we are today, trying to talk about generalization. So what is the scope of what we want to talk about? So we want really to understand what are the general laws that constrain inductive learning. What learning problems can be solved, or is it even a legitimate question? Is something can be learned versus can something not be learned? And when can we trust the output of a learning algorithm? So more specifically, we want to have some theory that relates the probability of successful learning, the number of training examples that we observe, the complexity of the hypothesis space we are using, the accuracy of to which we want the target to be approximated, and perhaps also the manner in which learning examples are presented. So hopefully you see that all these bullets are related to quality of learning in the past and in the future, and we want to be able to relate them. In fact, we're going to talk about all of them with the exception of the last one, although it also matters, but I'm not going to talk a lot about it. So just to remind you where we are, so I'm going to show a few slides that you already saw, just to bring everything to the top of your head. So if you remember, we said that we want to be able to say something rigorous about learning algorithms, and we want to talk about the number of examples one needs to see before we can say that what we've learned is good. And this is different than what we've done before when we learned conjunctions. So when we learned conjunctions, for example, we talked about, okay, so how many examples are needed in order to learn it? But really what we did is how many mistakes we're going to make before we learn it. And we did it in 3 protocols, right? Hopefully you remember we talked about a protocol where the learner proposed instances as queries. So the learner really controls what the observations are. Another protocol where the teacher controls the observations. And finally, we got to this protocol 3, which is our dominant protocol, which is random source of examples. And we talked about the first one. We saw that it's actually pretty good. All we need is just 6 examples. And then we talked about the second one. Oh, sorry. The first one was 100. This one is only 6 examples because the teacher was good and presented really useful examples. And then we finally got to protocol 3, where we developed an algorithm for conjunctions. And I know that you remember this, but I'm going to remind you nevertheless that the algorithm was a very simple algorithm, right? So we basically said we're going to call it elimination because we start with the set of all possible literals. And as we see examples, we eliminate those that we know for sure cannot be part of our final hypothesis. So specifically, because we know it's a conjunction, we eliminate the literal that isn't active in a positive example. So for example, when we see this example, all ones, positive example, we learn nothing. We still with the list of all conjunction, all literals. This is a negative example. We learn nothing from it. This is a positive example that has a few active features and a few non-active features. We learn that all these non-active features are not there. So we update our hypothesis. Now we have x1 up to x5 and x99 to and x100. And then we learn another negative, another positive that shows us that x99 isn't there. So now we have this one, and that's where we are done. So the final hypothesis is this: x1, x2, x3, x4, x5, x100. And we knew that this is actually wrong, right? We knew that x1 doesn't belong there, but we didn't get any example that eliminated it, so that's where we are. And the question we want to address is, or we did address the question of the number of mistakes we make before reaching the exact target function. We talked about that. And in fact, you also talked about it in the homework. But we don't know how many examples are needed to guarantee good performance. And by good performance here, I mean what's going to happen on the next example. Currently, you don't know what's going to happen. It could be this example or one of these examples on which I'm making a mistake. It could be an example on which I don't make mistakes. And we don't have any tools to tell us, to say something about what's the probability one of these scenarios will happen. Agreed? Okay, so then we said that we can go in 2 directions. This is one, mistake-driven algorithms. And there are some good things about it because it gives us some ability to quantify what we are doing. Or we could continue analyze this probabilistic intuition, the following probabilistic intuition, and this is what we're going to do today. So here is the intuition. The intuition is as follows. So we never saw x1 in a positive example, right? That's why it stayed in the hypothesis. Maybe we'll never see it. Maybe it so happens that in the distribution of examples we are exposed to, x1 is never on in a positive example. So if we will see it, it will probably be with a very small probability because so far we've observed a lot of examples and it never happened. So we don't care, right? What we've learned so far is still pretty good. and good in terms of performance on future data, right? Because under the assumption that what we've seen is what we're going to see in the past, maybe it's going to be okay. And this is what's going to lead us later today to define this PAC framework for probably approximately correct, where we're going to quantify these things. Okay, so just a little bit of notation. We're talking about instance space, or space of examples. We're talking about a concept space, or a function space, that contains the set of all possible target functions that we can imagine. So the target function, the hidden target function, is a member in this collection of functions. The target function f, you can think about it as the set of all conjunctions, or the set of all n-dimensional linear functions, or the set of all n-dimensional quadratic functions, or anything else. We have a hypothesis space. This is the space into which we are learning, right? And in principle, C and H are different spaces of functions. Each one of them is a collection of functions, but they are different. We have a collection of training instances. The set S is a subset of X, cross with 0, 1, or minus 1, 1 if you want, of positive and negative examples. And our goal is to determine a hypothesis H in H such that H of X is equal to F of X. Okay, so far? Now we need to add some quantifications. And the quantification is on X. What do we mean when we say H of X is equal F of X? For what X's? One option is training. So we want to find, so under this option, we want to find a hypothesis H in H such that H of X is equal to F of X for all X in S. Is that what you really want? You want it to be for all X in X, right? Because for all X in the training set, maybe it's not a big deal. You care about what's going to happen on those X's that you haven't seen so far. So this is really what we want. First of all, it's important to notice that these are two distinct questions. Okay, so remember, we did it here for all X in S. But we know that it's not going to happen for all X in X. Right? So these are two different things. Really what we want is to refine this a little bit. We want to say that we have training instances, positive and negative example of the target concept, where these instances are generated by some fixed but unknown probability distribution over X. Fixed, it's important that it's fixed, because if it's not fixed, who knows what's going to happen. But unknown, again, it's important because otherwise there's no learning problem. If you know the distribution, you're done. And under these conditions, which I now refine, I want to determine a hypothesis H that estimates F, evaluated by its performance on a subsequent collection of instances, or instance, that is drawn according to the same probability distribution. So now I made it a little bit clearer mathematically what I want. And again, this is to remind us where we are. So here is the situation we're at. So we've seen a lot of examples drawn according to D. Right? This is our universe. The way my notation here is as follows. A circle here is a function where all the points inside the circle are positive examples, all the points outside the circles are negative examples. Part of X, my universe, but outside, but negative for the functions, okay? So what you see here is disagreement between F and the hypothesis, right? So there are some positive examples of the hypothesis in this region that are negative for the function, and there are some positive examples for the function, the target function, that are negative for h. So that's the realistic situation, right? The general situation. Is this the general case here? Is this picture that I drew here a fair picture of this specific learning scenario of conjunctions? Yes. Why is it not a fair description? What is a subset of what? Okay, so let's talk about it in terms of positive and negative examples. So if an example is positive for h, can it be negative for f? If an example is positive for f, can it be negative for h? No. Right? So this part is empty for the specific case that we are talking about, conjunction. But in general, that's the picture. Right? And in fact, not only that's the picture, there is a distribution over this rectangle. The distribution is D. Don't be misled by the size of the regions. The size of the regions is the uniform probability distribution over the rectangle. It's not uniform because, for example, this moon have no examples in it. This moon looks the same size, has examples in it. So it's not uniform. I just don't know how to draw it otherwise. But this is important to realize, right? And maybe there are actually no examples at all outside here. Who knows? So there is some carpet, sort of some manifold over this that goes into the class that defines what's the distribution of different examples here. It's not uniform. But that's the general picture that we have. We have F, we have H, and we care about this symmetric difference, really, right? The error, according to a distribution D, is the probability that an example is in this symmetric difference. F of x is different than h of x. That's the game we're playing. Okay, so we want to be able to bound this error, basically given what we know about the training instances. So let's try to do it. So let's try to analyze and start by analyzing the case of conjunction. So as you all agreed, this is the right picture. I hope this is the right picture now for conjunction, but the picture doesn't matter. Let's think about, can I say something quantitative about this hypothesis? How good will it be in the future? So let's assume that z is one of the literals, and I'm going to denote by p of z the probability that z is false in a positive example that is sample for my distribution. Okay? Again, so z is a literal. There exists some probability distribution that z is false in a positive example, and I'm denoting this by p of z. Notice that in this case, the error of my hypothesis is bounded by the sum of p of z for all possible z's in the hypothesis. And we're going to argue this now, although hopefully you agree with me that this is true, right? So each z, I'm going to make an error if this z exists, right? Now, it could be that the worst case will be that every z like this is going to cause errors that are distinct from other z's. I'm going to suffer errors from all of them. Question?
G is a set of x and y, right?
I don't see. Z, you mean z?
Z is training instance, combination of input.
With the y, yeah. So it's an example that comes with a specific label, yeah. Okay, so what is P of z. P of z, I defined it to be the probability that z is false in a positive example. Given our algorithm, P of z is also the probability that z is deleted, eliminated from H in a randomly chosen positive example. So in fact, let me refine my answer to you before. I think the easiest way to think about now is there is a distribution over X. Let's not think about distribution over X cross Y, because the cross Y is deterministic, right? F is known. So let's just think about probabilities over X. I think it's much easier for us to think. So again, so P of z is the probability that z is deleted from H. Everyone agrees. If z is in the target concept, P of z is 0, right? Everyone agrees? Because it will never be false in a positive example. So P of z is 0. And my claim is that H will make mistakes only on positive examples. You already agreed with that. I'm just writing it again. A mistake is made only if a literal z that is in H but not in F is false in a positive example. In this case, we're going to predict that it's a negative example, but really it's a positive example. And therefore, P of z is the probability that z causes H to make a mistake. And the worst case, as I said, is that each z is going to cause its own mistakes. And different z's are going to cause different mistakes. They will never appear together. And therefore, my error is going to be the sum of the P of z's or over all z's that are in H. Okay? Comment there. That's not true. No, because we start with H, which is everything, right? And then we eliminate. We may not eliminate all of them, so we will still have some literals in H that are not in F. Right? This is the X1 here, right? Think about this X1. We haven't eliminated it yet. Okay? Yeah. Yeah. Z ranges over all 100 literals. Some of them have the property that P of z is 0. Some of them have the property that P of z is positive, non-zero. But basically what I'm saying is that once you fixed H, I don't know what is your H, but you fixed H. For each z, there is a well-defined P of z. Right? Given that the distribution is known, P of z is known. P of z is just this, the probability that z is false in a positive example. And my claim is that the error that this H that you fixed is going to make, this error is bounded by the sum of the P of z's over all elements in H. And we just proved that. Everyone agrees that we proved that? Question? On slide. The error is the same thing. Right? So what is the error? The error is the probability that f of x is different from h of x, where the probability is over the distribution from which examples are sampled. The same thing that I have here. The probability that the error of h is the probability that when I sample an example, h will predict on this example differently than f predicts on it, right? So both of them are exactly the same. Yeah?
So the error will actually depend on the sample surface.
Of course. The error will depend on the way, question, does the error depend on the probability distribution from which we take the samples? Yes, of course. Right? Because if, for example, I will never give you an example with x1 on in a negative example, this H will never make mistakes. But if I will give you a lot of examples where x1 is on and the examples are negative, you will make a lot of mistakes. Right? So the underlying distribution is very important. And you see it here in this picture, the probability measured under D. And you see it here, right? Because I define P of Z as a function of the distribution D. Okay? So two people here can have different Ds. Different Ds dictate different P of Zs, and therefore they dictate different errors. Okay? Okay, so we proved a simple claim that the error of the hypothesis, the error that you converge to a hypothesis, right? So the situation here is we learned. Now we have H. Let's analyze it and say something about it. For this H, we agree that this error is bounded by P. Let me continue with the argument, and we'll get back to the question. So now I want to distinguish between two kinds of Zs, bad Zs and good Zs. I'm going to say that Z is bad if P of Z is large. How large? I want it to be epsilon over n. If it's more than epsilon over n, I say that it's bad. A bad literal is a literal that has a significant probability to appear with a positive example, but nevertheless, it hasn't appeared in the training data, right? Because it is in H, even though P of Z is large. So I did not eliminate it, because it's in H, even though P of Z is large. Okay? So my claim is that if there are no bad literals, the error is less than epsilon. Why? Because we proved that the error of H is less than the sum of all P of Z's. If all of them are less than epsilon over n, their sum is less than epsilon. Okay? So if there are no bad literals, we're fine. We will never make more than epsilon mistake. You choose epsilon. Now let's see what happens if there are bad Z's. Yeah. N is the dimensionality, the number of features that we have.
But actually, after H, and after
Yeah, so it would be even less than epsilon, because the size of H could be less than n, right? No, I don't know what's k. The only thing I know is n. I know that my examples are of size n. I also know that probably the number of literal in H over which I'm summing here is less than n. But I'm not sure, maybe all of them stay there. So I'm saying that this is greater than epsilon over n. And here, for each P of Z, I put epsilon over n, and I'm summing. I will definitely get something that is less than epsilon. Okay, so that's if there are no bad literals. You choose a number. Let's say 0.1. Okay?
P of Z is probability over the sample that you have drawn, or is it over all the examples that are?
Over from D, right? So in D, in the distribution over all the possible examples, 2 to the n examples, let's say, this is P of Z.
So when
So Z is a literal. It's one, in this case, it's one of n options, right? And now, if you look at all the examples, if you could look at all the examples, you could ask yourself, let's go to the definition. What is the probability that x1, let's say z is x1. What's the probability that x1 is false in positive examples? Right? So if you had access to D, you could have counted, right? I don't know what it is. I'm just arguing about it. But it's a well-defined number given that D exists, right? Okay, so now we are arguing on the two cases of a bad literal and a not bad literal. And we agree that if there are no bad literals, we're going to be okay. We're not going to make too many errors. What if there are bad literals? So let's assume that Z is a bad literal, right? And this is my definition again. What is the probability that it will not be eliminated by a given example? Right? So it's a bad literal. Now I'm observing an example. If it's going to be there, it's going to be eliminated, right? So the probability that it survived this example is 1 minus the probability that it's eliminated, which is 1 minus P of Z. This is exactly the definition of Z, of P of Z. And this probability is less than 1 minus epsilon over n, because Z is bad. Okay? Now I'm going to do this m times, m independent times. And Z survived all these m trials to eliminate it. What's the probability that it survives those m independent examples? It's 1 minus, well, should be less than 1 minus P to the Z, P of Z to the m, which is 1 minus epsilon over n to the m. Okay? Now, what do I want? I want, so this is going to happen, right? Because if Z is bad, this event happened because it survived m independent examples. And I want to make sure that I choose m such that the probability of this event is very small. How small? I want it to be, okay, so just to clarify. So before we get to what I said, so this was for Z, 1Z. At most, we can have n bad literals. So the probability that some bad literal survives these m examples is bounded by n times this number. Okay? Basic union bound, sort of basic probability. Okay, so that's the probability that something could happen, something bad could happen, and I want to bound this. I want this to be small. Say I want to make sure that I chose m to be large enough so that the probability of this bad event will be bounded by delta. Right? So that some Z survives these m examples is bounded by delta. So I'm going to say the probability that Z survives m examples, which is this n times 1 minus epsilon over n to the m, is less than delta. And now I'm going to, basically what I want to do is I want to solve for m. Remember, what epsilon is the error that I'm willing to live with, 0.1. Delta is another probability that I'm willing to live with, right? 0.2. And I want to know, okay, so what should m be so that I'm going to live with this epsilon and delta? So I'm going to solve for m. In order to solve for m, just one technical thing, I'm going to use this inequality here. 1 minus x is positive here, is always less than e to the minus x. And you can prove it to yourself many, many ways. You can write the Taylor expansion of e to the minus x, for example. So it's 1 minus x plus x squared over 2, and a few other things. Or you can just do it directly. It doesn't matter. Convince yourself that this is true. But basically what it means is that I can replace this 1 minus x here, 1 minus epsilon over n, by e to the minus epsilon over n, and it's sufficient to require that this is less than delta to be safe. Okay? Again, I'm replacing this 1 minus x by e to the epsilon over n. And I'm requiring that this will be less than delta. So this is my requirement now. It's n times e to the epsilon over n to the power of m. And I solve for m. The way to solve for m, you'll do it yourself. You just take the log of the two sides, for example, and recover m. And you see that if m is greater than n over epsilon times ln of n plus ln 1 over delta, then you're safe. It means that the probability of failure, that is, that the error is greater than epsilon, is less than delta. Okay, so basically what we did, we proved the theorem. Here's the theorem that we proved. We said that if m is this, as above, then with probability that is at least 1 minus delta, there are no bad literals. Or, equivalently, if m is as above, with probability at least 1 minus delta, the error of my h is going to be less than epsilon. So that's what we wanted, right? So we started with knowing that we are playing with conjunctions. We ran a learning algorithm over some examples that someone gave us. We got to h. And then we asked the question, how good is h going to be in the future? And the answer is, with probability 1 minus delta, the error of this hypothesis is going to be less than epsilon, provided that you've trained it on these many examples. Questions? Well, we also talk about negative example. It so happens for the negative example P of 0, 0, so it didn't matter. But the statement is still holds. Right? It doesn't matter. You got to h, right? And my argument here is about this h. Yeah.
Right. So the definition of the error function.
Yes.
So how do we interpret the last statement?
Okay, so let's, epsilon is the error of the hypothesis, right?
Well, right, not the error means the probability.
Yeah. So I'm going to say this 7 more times today, so it will be clearer. But error, epsilon is the hypothesis error, and 1 minus delta is the probability over the scenarios that I have. I'm sampling data for my distribution D, and some samples are going to be good, and some samples are going to be bad. So my confidence in saying, so I'm going to tell you, don't worry, this hypothesis is good. It's making less than 0.1 mistakes, 0.1% mistakes. How confident am I that this is going to happen? 1 minus delta. So these are two different numbers. Let's do it again, and you'll see it. Okay, these are just some numbers. You can see that the numbers are high. Even for n equal 100, you need 7,000 examples so that your epsilon and delta are going to be 0.1. But notice that it behaves logarithmically in delta. So if you change delta to be 0.01, the number of examples doesn't change so much. Okay, so I want to keep on going. So I'm going to say the same thing that we said before. I'm just kind of formulating in a slightly more general way. Here is the game we're playing. We have an instance space, which is the input to our classifier. We have an output space, plus or minus 1, say. We are making predictions with the learned hypothesis H. We have an unknown distribution, X over X cos Y. Before, because it was conjunction, I just said let's put it on X. But this is the general situation. We have a set of examples that we draw independently from this distribution, and the size of the sample is M. Okay? Now, we can define two notions of errors. A true error, which is the error over the distribution D, the probability that H is different than the correct label. An empirical error is the error over S, that H is different than Y. And the question that we ask here is, can we describe or bound the error of D once we know the error on S? So far, what we've done, and we'll continue doing it today, we assume that the error of S is going to be 0. Right? So we actually learn something that is completely consistent with the training data. And then we ask, OK, so what's going to be the error over D? Later on, we're going to say, OK, error of S is not 0, is something. But still, we want to relate it to the error of D. That's question 1. Question 2 is a little bit more refined, more restricted perhaps, where we say, you know what? There is a function space, a collection of functions from which the hidden function comes. We call this C. So we have a set of possible target functions. Still, we have the hypothesis space H, and we're asking, is C learnable? Is it possible to learn functions that come from this collection of function C's? And the question of whether something is learnable, of course, depends on whether we can bound the error in the future as a function of the error on the empirical. Because if you can never bound the error, it means you cannot learn, basically. We're going to give a more subtle definition, but that's the bottom line, right? If you cannot bound the error of your hypothesis for a specific collection of target functions, you cannot learn these target functions. OK. So what are we saying here so far? We're saying, really, there's no way to learn a concept or a function exactly. Because, you know, generally, once you see a data set, there could be a lot of functions that are consistent with this data set. So unseen examples potentially could take any label. You have no chance to exactly learn it. Everyone agrees with that, I hope. Moreover, we cannot always expect to learn even a close approximation to the target concept. And the reason is that we sample the training data. And it could be that the sample wasn't so good, right? This is where the delta comes in. The sample wasn't good. You know, we wanted to find a good definition for elephants, but our sample only contained white elephants. Probably not the typical case, but that's what we've seen in the sample. We now think that elephants are all white, right? Now, this is not going to happen with high probability, because there is some distribution D, and it's unlikely that all your samples will take these weird examples, but this is where delta comes in. So our only chance is really to learn with high probability a close approximation. So this is, the close approximation is our epsilon, is how good is the hypothesis, and it's going to be pretty good with high probability, with high confidence, if you want. OK, let's get to details. Yeah? Yeah. Give me 3 minutes. Maybe we'll get there. If not, 2 days. So this notion of close approximation with high probability is what gives rise to probably approximately correct. So this is what I just said. And in probably approximately correct learning, we require that given a small parameter or small parameters, epsilon and delta, with probability at least 1 minus delta, our learner produces an hypothesis that has error at most epsilon. And it's important to note that the reason we can even hope for that is the consistent distribution assumption, the fact that what we've seen is what we're going to see in the future. Okay, this is the definition. And because you wanted to generalize, let's see, can I generalize? No, we'll start with it next time. So I'll just finish with the definition, and we'll generalize next time after you already mastered the case of conjunction. So this is the formal definition of PAC learnability. We consider a concept class, a collection of target functions, defined over X. We have a learner L that uses a hypothesis space H. So we're learning into functions in H. We say that C is learnable. Again, C is a collection of functions. It's learnable by algorithm L using hypothesis H if for all the functions there, I don't know which one is going to be the hidden function, so I have to do for all functions in capital C, for all distributions D over X, and for fixed epsilon and delta, my algorithm L, when it's given a collection of M examples that are sampled independently according to D, produces, with probability at least 1 minus delta, a hypothesis that has error at most epsilon. And I want to do this where M, the number of examples, is polynomial. It has to be polynomial in 1 minus epsilon, 1 minus delta, N, and the size of C. So first of all, convince yourself that it makes sense, right? So if you want epsilon to be tiny or delta to be tiny, you will need to see more examples. And it's natural also to assume that the dimensionality, the number of features, and the size of the function class make a difference here. The larger they are, the more example you'll have to see. In addition, there was no computational complexity here, so we can also say that we're going to say that C is efficiently learnable if we can do all this also in time that is polynomial. And we'll see that these two conditions of general learnability, which we call sample complexity learnability versus time learnability, they are not exactly the same thing. It could be one without the other. So next time what we're going to do is we're going to generalize as you wanted and give a very simple proof that something like this is doable, not only for conjunctions, but also see that it's not always doable. Okay, so we'll continue on Thursday. Sorry.
Independence assumption come into play here?